In this video, we're going to go through a number of examples applying logarithms to help us solve problems of exponential growth and decay. Here's the first example from our handout. So we've got this function, and it models the population of India in millions X years after 1974. All right, so that's key information. The output is going to be in millions. The input we have to talk about in years after the year 1974. So the first part wants to know, what did the model predict for 1994? Now this is just a model. It's not going to be an exact amount, but it might be a fairly accurate prediction. So what we want to do is we want to plug in 20 for X in this case, because we want 1994. That's 20 years after 1974. So we're going to plug in 20 for X, take a calculator or computer and compute that number, and we get approximately 959 million. Okay. Now, same kind of question, how many people for 2009? So 2009 is, in this case, 35 years after 1974. Just do 2009, subtract off 1974, and you get 35. So we're going to plug in 35 for X, compute, and in this case we get approximately 1,410 million people. So for the first two parts of this question, we're just given an X value, and we need to plug in and determine the corresponding output value. All right, the next couple of parts are a bit different. The third part wanted to know, in what year does the model predict the population of India is going to exceed 1 billion people? All right, now for that, we need to convert first billions into millions. So the first thing to notice is 1 billion is 1,000 million. Now, millions of people, that's standing for the output variable, in this case f of x. So we want to let f of x equal 1,000 and then solve for x. So we're going to put 1,000 in there. Now we want to solve that equation for x. We're going to divide both sides by the 574. They cancel out on the right hand side, just leaving us with 1,000 over 574 equals 1.026 to the x power, or we could rewrite that as 1.0626 to the x power equals 1,000 over 574. Now here's where logarithms come involved. We can't solve that algebraically. We have to convert this from exponential form to logarithmic form. Just to remind you of our conversions, there it is. Right? Log base b of u equals v is equivalent to saying that's the exponent we have to raise b up to obtain u. So in this case, b is 1.026, v is x, and u is the 1,000 over 574. So that converts over to x equaling log base 1.026 of 1,000 over 574. Now we can't compute that directly. We're not going to be able to do that one in our head. So what we need to do is apply the change of base formula here. The change of base formula is going to say that's equal to the natural log of 1,000 over 574 divided by the natural log of 1.026. And that's something we can compute with a calculator, scientific graphing. On a graphing calculator, you can use the log base button also to do that directly, but if you don't have a graphing calculator, you can just use a scientific calculator with the ln button on it, or you can just use the ln button directly off the graphing calculator. And that's how we answer the third part of the question. The last part wanted to know by what percent does the population increase from one year to the next. For that, we got to remember that for these exponential models, we can always take the base and write the base b as 1 plus a number I've called capital R, where that represents the percent growth or decay. So in our case, we're looking at our base being 1.026. So we can set that equal to 1 plus r, and then solve that linear equation by subtracting 1 from both sides to get that r is, in this case, 0.026. Converting that to a percentage, we get it's increasing by 2.6% from one year to the next. So that finishes the first problem. There's 4 parts to it. Second problem, maybe a little bit shorter. They give us the growth model for a bacteria. This time x is standing for time in minutes. What we want to do first is figure out by what percent the population increases each minute. So to do that, we want to do a similar thing to what we did in the last part of the first example. Rewrite the base as 1 plus a number. That 1 stands for 100%, and then you're either adding or subtracting off a certain percentage. In this case, R is 1.5. Converting that to a percentage by moving the decimal place 2 to the right, we get 150%. So the bacteria in this case is growing by 150% each minute. Now the second part of the problem wanted us to find out how long is it going to take for the population to reach 30,000 cells. In this case, we want to input the number 30,000 not for x, because that stands for time, but for g of x, and then solve the equation for x. All right. To do that, we're going to isolate the expression that's involving the x. That is only the 2.5x, right? The exponent x in this case does not affect the 500. So we're going to divide both sides by 500, then simplify to get that 60 equals 2.5 raised to the x power, or 2.5 to the x power equals 60. Then we want to again convert from exponential to logarithmic form. So this is going to say that x is equal log base 2.5 of 60. That's an exact answer for the question, but if you want to approximate this with a decimal, you're going to have to use the change of base formula. So we're going to say it's the natural log of 60 over the natural log of 2.5, and that gives us about 4.468, etc. minutes. Okay, for the third question, we wanted to solve this banking problem. If you got $10,000 and if you invest it at 3% interest, and that's compounded monthly, so the 3% is your APR, and you are going to earn interest each month in this savings account. We want to know what's the balance after 10 years. So for that, we're going to first write the formula down. All right, and this is our banking formula. P stands for the principal, R the interest rate as a decimal, and N the number of times you compound per year. T is time in years. We're going to plug our information in. P is 1,000 or 10,000 in this case. R is 0.03. N is 12. Now just simplifying in the inside, it comes out to a nice number. 1 plus 0.03 over 12 comes out to 1.0025. Makes our formula look a little bit easier. Now the first part's pretty easy to answer. All we need to do is plug in 10 for T. 10 stands for a time in years. So plug that in, and then take a calculator to compute, and you get it's about $493.54. So that's it for that one. That's the easier type of question to answer. When you're given the T value, it's a direct plug-in. If you want to know what is the balance, or how long it's going to take, for the balance to get up to a certain amount, then you have to solve that by logarithms, which is what the second part of the question is asking. How long will it take for the balance to get up to 25,000? For that, we need to put in 25,000 for the balance, not for T. And then we're going to solve it for T. All right, now for that equation, again, the exponent 12T only affects the 1.0025, the base, so we can divide by 10,000 and then simplify. It gives us 2.5 is equal to 1.0025 to the 12T, or we can write it in the other way. And now we want to convert from exponential to logarithmic form to then isolate T out of the exponent. So we get 12T equals log base 1.0025 of 2.5. And then we want to solve this resulting linear equation for T by dividing by 12. And that gives us our answer. That's a perfectly fine answer unless you want a decimal approximate. For that, you're going to have to use, again, the change of base formula. So you just apply that in the numerator to get the natural log of 2.5 divided by the natural log of 1.0025 over 12. And that is approximately 30.5812 years. And that finishes the third question.